to educate the community of scientists regarding these great technologies. We are providing various education sort of sessions, such as journal clubs, seminars, symposiums, and these TPCF webinars, which of course they're free of charge, these webinars, and we want to create a platform where scientists who are interested in preclinical imaging would gather and start discussing about very interesting topics in this multidisciplinary preclinical imaging. Our website is tpcf.ir, and I would ask the TPCF admin in case if she could actually put our website as well and our contact information in the chat. Can I ask everyone to switch off their webcams, their microphones? If you want to ask any questions, please direct them towards me, TPCF host, and I will ask Dr. Julia Mannheim at the end. Or if you want, you can actually raise your hand and we could give access to your webcam or microphone, and you can ask your question orally. With that, these housekeeping sort of rules, I would go and introduce our great speaker for today's session. So Dr. Julia Mannheim, we are honored to have her to be discussing about standardization for preclinical imaging, which is a very, very important part of this multidisciplinary sort of area. So Dr. Mannheim, she's the Deputy Director of the Department of Preclinical Imaging and Radiopharmacy, and she's a postdoc research fellow and group leader of PET and nuclear and optical imaging sciences at the renowned Werner Siemens Imaging Center in Germany. And it's an honor to have Dr. Julia Mannheim this evening. Her research interests are PET and SPECT and CT evaluation, as well as standardization of small animal imaging. Dr. Julia Mannheim, the platform's all yours. We would be happy to hear your lecture. I think you need to unmute yourself as well. If the admin could actually help Dr. Mannheim to give access to her microphone. On the bottom left corner, Dr. Mannheim, there's a microphone button. If you can press it, should be working. Actually, I might be able to do it as well. Let me try to find you. Not managed to.
Okay, hello everyone.
We can hear you loud and clear. Thank you very much.
Thank you very much. So now I'm a co-host and I'm able to turn on my microphone. Thank you. Thank you very much for this very kind introduction to give this webinar today. I will start sharing my screen so that we basically can start right away with the webinar. Okay, so can you see my slides?
Yes, I can see your slides.
Perfect, thank you. So I will also turn off the webcam just for during the talk, and then later on turn it back on just for communication.
Yeah, however you're comfortable, that's great, thank you.
Perfect. So again, thank you very much for this very kind introduction to give this webinar today. And the focus of this webinar is preclinical standardization, the current status and future prospects. So as an outline of my talk, I would first like to discuss what is standardization and why do we actually need it. Then I would like to discuss the terms reproducibility, reliability, and repeatability, since these three terms always come up when we talk about standardization. Next, I would like to give some examples from the literature in regards to standardization of animal handling, as well as of positron emission tomography, and then also image analysis. And at the end of this webinar, I would like to briefly introduce you to the RIVE guidelines. So these are guidelines specifically made for animal research, reporting of in vivo experiments. So when you prepare a manuscript, these guidelines will help you to include all the necessary information that you need to provide in order for other people to reproduce your study. So starting with what is standardization? So over the last decades, there's been a huge discussion about standardization, both in the preclinical research, but also in clinical research. So when we talk about standardization, multiple terms always come up, as already mentioned: reproducibility, repeatability, but also accuracy, quality control, standards. So it's really that the term standardization is made of multiple terms together. And when we Google the term standards, Wikipedia comes up with the definition that it's the development of technical standards based on the consensus of different parties. So that means multiple parties come together, so firms, user groups, governmental agencies, they develop and define technical standards. And once they are set in place, everyone should follow along these standards. But what is the advantage of such standards? Well, it's to mandate the quality and consistency of technologies and hence also of the acquired data. And it ensures their compatibility, interoperability, and safety. So it really helps you to strengthen your data and to really have a more standardized, harmonized protocols in place for your technologies. However, there's been a huge discussion lately going on about standardization. Why do we actually need it? And there have been a couple of high-ranked published manuscripts over the last couple of years stating such comments as biomedical research, increasing value, reducing waste. The next one states why most published research findings are false. Another one basically says, believe it or not, how much can we rely on published data on potential drug targets? The next one stating, in search of preclinical robustness. Another one, or another example is avoidable waste in the production and reporting of research evidence. And also the last example that I would like to give is how to increase value and reduce waste when research priorities are set. Of course, all of these are very provocative statements, but there is a certain truth in these statements that we have problems in reproducing our research data. So, and Beckley et al. State that in 75 to 90% of basic and preclinical research can simply not be reproduced. So that's been, when you think about this, this is 3/4 or even more of the data that cannot be reproduced. And they also state that 85% of the biomedical research is waste. Of course, again, very provocative statements, but there is a certain truth in this that we have really problems in reproducing our data and making it more reliable and strengthen our research data. And another example that I would like to give from the literature is from Prinz et al., where they tried to reproduce the data that was published in approximately 65 different manuscripts. So these were from 3 different research areas, so oncology, women's health, and cardiovascular, and they tried to reproduce the data or the results from these manuscripts with their in-house methods. However, they found out in 67% of the cases, they had to adapt the model to internal needs. Otherwise, they weren't able to reproduce the data. And in only 21% of the cases, they were able to reproduce the model one by one. And the reason why they weren't able to reproduce the data from the published papers one by one was that they mentioned that, or they stated that there were simply in 65% of the cases, there were inconsistencies in the data. These can be avoided by a proper manuscript reporting, and by having standardized and harmonized protocols in place to enhance the reproducibility and reliability of data and results. So there are a couple of initiatives already in place to enhance the standardization and the harmonization. And I would just like to give a couple of examples here. For example, the imaging biomarker roadmap that specifically focuses on cancer, but also the ERNM PET-CT tumor imaging guidelines using FTG, then the PERSIST guidelines for tumor imaging, as well as the Consortium for Reliability and Reproducibility, but also, for example, the Quantitative Imaging Biomarkers Alliance. And then there are also clinical PET, CT, and MRI accreditation programs around, and I will focus on this a bit on the next slide. These initiatives all focus on clinical imaging. There is also the ESME study group standardization of small animal imaging that specifically focuses now also on preclinical imaging. So it is definitely worth checking out those different initiatives and their protocols, how to have a more standardized and harmonized imaging in place. Moving on now on focusing a bit more on the clinical accreditation programs. So these are available for a variety of clinical modalities and applications, and their goals are to set quality standards for imaging practices, to meet the requirements for equipment, medical personnel, and quality assurance, and to enhance the comparability of data acquired. So this is especially true in a multicenter approach. So that means when you want to perform a multicenter study and all of the scanners within those different centers are accredited, then this definitely will help you to enhance the comparability of your data. In order to get accredited, you need to provide information on staff, guidelines, and regulations, as well as we need to acquire phantom data that will be evaluated by the accreditation program. However, the problem is that these are only available for clinical modalities. So this is in sharp contrast to the preclinical field, where we currently have no official accreditation programs set in place. So this is definitely something that we are lacking in the preclinical field to enhance multicenter standardization or harmonization of data. Moving on to the three terms that always are discussed in regards to standardization: the reproducibility and reliability and repeatability. So these three are all requirements for quantitative imaging. And focusing first on the repeatability. So this is measured in one patient subject using the same imaging system. So when you perform a scan on day 1 of one patient and you scan the same patient on day 7 with the same imaging system, you're getting the same result, then you have a very high repeatability of your data. If you're not getting the same result, then of course you have a very low repeatability of your data. Reliability, however, is the difference between two acquisitions on the same subject. So this means when you scan the same subject using the same imaging system again on 2 days, and you have a very small difference between the two acquisitions, then you have very reliable data. If your difference is, however, very large, then you don't have very reliable data. And the last term is the reproducibility of performance, analysis, and interpretation. So that's between patients, subjects, systems, and institutions. So when you're scanning one study, or when you're performing one study in your own laboratory, and then another site wants to perform the same study and following along your protocol, if you're getting the same results, then you have a very high reproducibility of the data on a multi-center level. And all of these three terms, or all of this you want to achieve for quantitative imaging. And in order to achieve a very high repeatability, reliability, and reproducibility of your data, standardization and harmonization of imaging procedures are essential and can really help with this. So when we look at the typical study flow for in vivo imaging, whether it's preclinical or clinical imaging, what we usually need as a first prerequisite is that we need to have proper quality control standards in place and a proper calibration performed as well. So without having those set in place, you won't be able to get repeatable and reproducible results. The next thing that we need for in vivo imaging, especially in regards to PET imaging, we need the imaging probe to be prepared. So that means a tracer, or for CT and MRI, you also need contrast agent. So that means also you need to have proper protocols in place for the labeling of the imaging probe, but also in preparing the imaging probe. If you don't have standardized protocols in place for this, then this can also impact your in vivo imaging data. Then as a next step is, especially in regards to preclinical imaging, is the animal handling before and during the scan and the animal model. So you need to choose a proper animal model for your desired application, and also the animal handling before and during the scan can impact your in vivo imaging data. But also the animal model itself can impact your animal handling. So depending on which animal model you choose, also the animal handling needs to be, can be impacted by this as well. So as a next point, the administration of imaging probe then to move forward with the scanning. So depending on how you administer the imaging probe, this can also impact your in vivo imaging data, and also the animal model, depending on which you have chosen, then also the administration of the probe can be different depending on the animal model. But then finally, you can perform your in vivo imaging scan in a standardized manner. And if you have all of these different aspects standardized and harmonized, then you can ensure that you have repeatable and reproducible results. And usually after an in vivo imaging, especially in the preclinical field, we also perform ex vivo examinations. These can be, for example, biodistribution, omics, histology, but also further ex vivo tests. And especially the animal model and the animal handling can also impact your ex vivo outcome. So that means when you want to have some reproducible ex vivo outcome, you also need to ensure that your animal handling is standardized and your animal model as well. So I would now like to give a couple of examples from the literature, first in regard to animal handling and anesthesia. So this is an overview or a review from Van Hove et al., where they list frequently used anesthetics in small animal imaging. However, I would like to draw your attention to the second column, which basically shows the interaction with various parameters depending on which anesthetics you use. So for example, focusing on the first one, isoflurane. So this is a very common anesthetics used in small animal imaging. However, isoflurane can interact with various neuroreceptors and other proteins involved in neurotransmission. So when you're studying or investigating neuroreceptors, then maybe isoflurane is not the best choice as an anesthetics for your study, because it can automatically alter or just directly alter the neuroreceptors. Another example that I would like to give is pentobarbital as so this interacts also as a GABA receptor agonist. So when you're investigating the GABA receptors, then maybe pentobarbital is not the most appropriate choice as an anesthetics. So it's really depending on what kind of, what your study design is and what you are investigating, you should choose the appropriate anesthetics for your study. Another example from the literature in regards to animal handling is now the temperature, the warming of the animals during a scan, or especially during an uptake phase of PET tracer. So this is an example from Füger et al. From the literature in regards to PET imaging and animal handling. And what they did, they performed PET FDG scans with a reference animal handling condition. So in this case, the animals were not fasted, they were not warmed during the anesthesia, during the uptake, and they were also awake during the anesthesia. And on the left side, you see the corresponding FDG PET image for this. On the right side is a CT for anatomical reference. So with this reference conditions, you have a very high uptake of the tracer in the brown fat tissue, but also in the brain and in the left ventricle. And what they now did is they started to change the reference conditions. So basically, they changed one of those parameters in having the animals warmed during the uptake phase. So in this case, you see immediately that the uptake pattern significantly changes, with having less uptake in the brown fat tissue, but increased uptake in the brain, and you still have an uptake in the heart. So by just changing one of these parameters, having the animals warmed, you significantly change the uptake pattern. As a next thing is they have the animals fasted overnight, but still not warmed and keeping them awake during the uptake phase. You see that again, you have an increased uptake in the brown fat tissue and still a high uptake in the brain. As a next condition, they tested they investigated the uptake patterns when the animals were fasted and warmed but awake. And here you see now that you basically have no uptake in the brown fat tissue and no uptake in the heart, but a very high uptake in the brain. And when they performed a conscious injection for the tracer injection, so that means when the animals were awake also during the injection, you see that you have a very high unspecific binding in the muscle areas. And then they also focused on different anesthetics for the uptake period. So this is an image where the animals were not fasted, but warmed with isoflurane. You see that you basically have no uptake in the brown fat tissue and also only a small uptake in the brain, but a very high uptake in the heart. A similar pattern when the animals were also fasted. And when they used different anesthetics, in this case ketamine, you see also that the uptake pattern changes with having an increased uptake again in the brain. So by just changing one of these parameters, you change significantly the uptake pattern. And this is definitely something that you need to keep into account and keep in mind. Another example in regards to animal handling is the circadian rhythm of the animals. So this is an example from the literature from 2001, and I apologize for the low quality of figure. However, that's a very straightforward example that I would like to show here. So what they did, they investigated 3 different mouse strains, so like 6 mice, BIPC mice, and CB6F1 mice. And they determined the blood counts at multiple times throughout the day. So at 10 a.m. and then also in the afternoon, in the late evening, and also during the night. And they determined the white blood counts, platelets number, and red blood counts. And by just looking at those graphs, you can immediately see that the blood counts change along or throughout the day. So depending on what time of the day you measure them, they are significantly different. And this can also impact your in vivo imaging data. Another example in regards to the circadian rhythm is now focusing on PET imaging. So this is an example from Van der Veen from 2012, where they performed FDG PET scans at multiple time points throughout the day. So at 6 a.m., at noon, at 6 p.m., and at midnight. And they determined the uptake in the brain. The animals were handled exactly the same way. The only difference is that they were scanned really at multiple time points throughout the day. And by just looking at those images, you directly see that you have the highest FDG uptake at approximately 6 p.m., whereas you have the lowest uptake at approximately midnight. And they also quantitatively analyzed this with the standard uptake value. So here also you see that you have the highest uptake around 6 p.m. and the lowest uptake around midnight. So depending or based on this, you should perform the experiments at the same time throughout the day. Focusing now more on the quantitative analysis of PET. So of course, as you all know, PET requires counts, and they are usually converted in activity units by proper calibration, and then you will end up with megabecquerel per milliliter or millicurie per milliliter values. Then you can calculate the injected dose per cc by dividing the activity in your region of interest with, by the injected activity of your animal. A more frequently used measure for the quantitative analysis, especially in the clinical environment, is the standard uptake value. In this case, you normalize the percent injected dose by the body weight. However, there are multiple ways how to calculate the SUV, as already shown by normalizing it to the body weight, but also you can normalize it to the body surface area or to the lean body mass. And this is really important also when you prepare a manuscript to include this, how you calculated the SUV. And it can also have a significant impact on your study results. So this is an example also from the literature here, where they investigated the differences between those 4 different SUV measures. So the SUV max, SUV mean, SUV peak, and SUV total. This is now a clinical example, but it also, of course, applies to preclinical imaging. This is an example from Van der Hoek et al., where they performed multiple scans before and mid-treatment and after the treatment of a tumor. So on the left side, you see the corresponding PET-CT images. And on the right side, you see the SUV over time. So basically what they did is they performed 3 scans. So week 0 was pre-treatment, week 2 was mid-treatment, and then week 3 was post-treatment. So in week 0, since they normalized the SUV, they had no differences, obviously, between those 4 SUV measures. However, in week 2, mid-treatment, they see that they have differences depending on different values of the SUV, depending on which SUV measure they use for image analysis. However, all 4 of these SUV measures are still in the same clinical assessment category, which says it's a partial response to the therapy. In week 3, however, now they see that they have significant differences between all those 4 SUV measures, with 2 SUV values indicating it's a progressive disease, 1 indicating it's a stable disease, and 1 indicating it's a partial response. So depending on which SUV measure they use, this will have a significant impact on the patient and especially on the therapy planning, because if 2 of those SUV measures say it's a progressive disease, then obviously the therapy plan might change. With 1 of the SUVs saying it's a partial response, then also the patient outcome can potentially change. So this really has an impact on the patient and needs to be kept in mind. When we focus now more on PET, there are multiple factors that can influence the quantification. And this is a review from Ronald Böllard, which I would really recommend to read if you're focusing or if you're doing PET imaging. What he lists 3 categories of factors that can influence your data. First of all, technical factors. So basically, he lists multiple factors that can influence your quantitative outcome. For example, the calibration between PET scanner and dose calibrator, but also residual activity in a syringe and so on. And he also gives a typical range of the effect, what to expect basically based on this factor. And you see that some of this factor only impact like up to 10%, but some of them can be really up to 50%. So this is something that you need to keep in mind, that some of those factors can have a significant impact on your outcome, and you should make sure that you standardize your protocols. So most of these errors or factors can be avoided by proper calibration of the used equipment. And in regards to clinical quality control, so there are multiple phantoms available to assess, for example, the homogeneity, recovery coefficients, or noise. So this is one of the phantoms that you can use in the clinical environment, where you have a homogeneous cylinder and then you have 6 fillable spheres placed inside the cylinder, and then you can determine the recovery coefficients, homogeneity. This is also another phantom, which is similar to the one on the left, where you also have fillable spheres inside the phantom to determine recovery coefficients, but also noise. And then using this phantom longitudinally, so if you repeat those acquisitions longitudinally, you could also assess if your scanner is acting stable over time. Of course, for preclinical fields, you also have multiple phantoms available. This is more or less a similar phantom for the preclinical field, where you also have homogeneous regions to determine the homogeneity and noise, but also you have 5 different watts that you can fill to determine the recovery coefficients. And then you also have multiple other phantoms available. So these are, for example, the upper part of the picture shows homogeneous phantoms that you can also use to calibrate your system and normalize your system. So with having proper quality control procedures in place, you can minimize those technical errors that Böllard et al. Mentioned. The second category that he also mentioned in his review are the biological factors. So multiple factors based on the biology can impact your outcome as well. So for example, the blood glucose level, the uptake period, but also if the patient or the animal moves and if there is inflamed tissue. And they also list the typical range of these factors. So some of them are on the low side in regards to the impact. So for example, just like 5 or 10%, but some of them can be up to 30 or 60%. So of course, those biological factors can be tracer dependent. So this is an example now for FDG tumor imaging. Of course, if you're using another tracer, you should determine those biological factors. So for example, when you're studying the neuroreceptors, as shown before, then maybe isoflurane is not the best choice as an anesthetics, and so on. So really depending on your study design, you should make sure that you have those biological factors stable over time. And the last category that they mentioned are the physical factors. So for example, the scan acquisition parameters, image reconstruction, but also the region of interest that you draw to segment your tissue. So typical range here is also, some of them only have like a low impact on the results, but some of them can have a really significant impact, so up to 75%. So this is something that you need to keep in mind, and you should always use the same parameters for all scans so that at least within your study, you are able to compare the data. And then when you properly report all of your parameters, then also other sites are able to reproduce your data. So focusing now on a preclinical multicenter study that we initiated here from Tübingen. And our aim was to determine the reproducibility and comparability on a multicenter level. So that means we asked 4 laboratories to participate in the study. And we asked them to use the default imaging protocol. So the only prerequisite that we gave them is they should scan 10 healthy animals with PET FDG after a 60-minute uptake period. Besides this, everything should be there followed along their default or using their default imaging protocol. So how they handle the animals, how they perform the heating or the temperature warming of the animals, how they determine the blood glucose levels, everything else should be really their default imaging protocol. And then we asked them to scan 10 healthy animals. These are qualitatively results of representative images from each laboratory. And by just visually looking at those images, you immediately see that, for example, laboratory D has a very low uptake pattern in comparison to the other 3 laboratories, whereas laboratory A and B seem to have similar uptake patterns. So again, these were not standardized protocols and you have different uptake patterns. Of course, we also quantitatively analyzed the data, starting with first the glucose level. So here, this graph represents the glucose levels for all 4 laboratories. And we have the highest glucose levels determined in laboratory C and the lowest glucose levels in laboratory B, with significant differences between those 2 labs, but also significant differences between laboratory B and D. And just to remind you, so these were 10 healthy animals. So in theory, with the same strain, same age, same sex. So in theory, we would expect that the glucose levels of all animals are exactly the same. However, we do see significant differences between some of the labs if the labs use their default imaging protocol. Moving on to the PET quantitative analysis. So this is the brain uptake here, again, for the 4 laboratories. And we do have the highest brain uptake in laboratory C and the lowest uptake in laboratory D, with significant differences also for most of the labs. And especially laboratory A and D also have significant differences between the brain uptake values. And this is something that we will focus on in the second step of this study. And then we also determined the muscle uptake, since especially for FDG imaging, the muscle tissue serves as a reference tissue where the uptake pattern should not change. However, here we also see that we have significant differences in the muscle uptake between laboratory B and D and laboratory C and D. So again, by not having standardized protocols in place, there are significantly different quantitative results. So moving on now to the second step, where we standardized the imaging protocol, and we only had 2 labs participating in this second step. So we performed the experiments in laboratory D by using their PET scanner, and then we tested or investigated 3 different conditions. The first one is the protocol from laboratory D was used, as well as the equipment from laboratory D, and the personnel from laboratory D performed the scans. As a second condition, we asked the personnel from laboratory D to scan those 10 healthy animals following along the protocol from laboratory A, but they still should use their own equipment. And as a third condition, basically the personnel from laboratory A went to laboratory D and performed the scans there with using their own equipment and following along their own protocol. And the image analysis was performed by 1 person in this second step, just to have not an impact on the image analysis on the data. So first of all, looking again on the glucose levels. So just to remind you, these were the 3 different conditions that we tested in laboratory D. So this is the protocol from laboratory D, and this is the protocol from laboratory A, but scanned by different personnel and using different equipment. So we still have significant differences in the glucose levels between those two imaging protocols. However, as soon as the same imaging protocol is used, we get reproducible and comparable glucose values. So this is now really important to emphasize. Although different equipment was used, so also different equipment for the glucose level, so for determine the glucose levels was used, but we're still getting comparable results as long as the same animal handling procedures are followed. Moving on with the brain uptake. So here again, we have the 3 conditions in laboratory D, but we also compared this now to the scans that were performed in laboratory A. So we are still having significant differences when the same imaging protocol was used in laboratory D, but the scans were performed by different personnel and different equipment. So it still seems here that for the brain uptake, also the equipment has an impact on the brain uptake values, but potentially also the personnel. So this is something that needs to be further investigated. However, as you can see, we are definitely getting closer with the brain uptake values. So they are more comparable, but still not reproducible. However, interestingly, we were able to have, reproduce the data that was acquired in laboratory D from the personnel from laboratory A in comparison to the data in their own lab. So here we have comparable and reproducible results on a multicenter level when the same imaging protocol was used, the same equipment was used, and the same personnel performed the scan. And we also looked at the muscle uptake again. So here we had no significant differences between the 3 conditions in laboratory D compared to the scans that were performed in laboratory A. So by having a standardized imaging protocol in place, this really helps to improve the repeatability of results. However, especially in regards to the brain uptake, there seemed to have also been an impact of the equipment, potentially also the personnel performing the scan. So this is something that definitely needs to be further investigated, but at least we are getting more comparable data. And as a third step now, we determined the reproducibility of the image analysis. So basically what we did is we used the 3 conditions from that were scanned in laboratory D, and then we asked the 2 independent researchers to analyze the data, following along the same material and method section. So this is basically what we end up. So we have, again, those 3 different conditions that were scanned in laboratory D. And then we have 2 people analyzing the data. So for the brain uptake, we were able to reproduce the data when 2 different persons analyzed the scan. And the reason for this is for the brain uptake, we used co-registration to anatomical data. So that means the PET scans were co-registered to an MRI or a CT image. And then the region for the brain was drawn on the anatomical data and transferred to the PET. So this resulted in a very reproducible image analysis. As a next step, we also determined the reproducibility of the image analysis for the muscle uptake. And here, for the first condition, we see that we have significant differences between the 2 persons analyzing the data. And for the muscle uptake, a manual segmentation was used. So that means the region of interest was manually drawn on the images. So, and also you see here that the variability, especially for analysis 2 or for the person that performed the analysis 2, is much higher than for analysis 1. So it seems that with manual segmentation or manually drawing the region of interest, you can introduce significant differences in the results. And then we also looked at the left ventricle uptake. So here a thresholding method was used, and you see that we have significant differences between all 3 conditions between the image analysis from the 2 persons. So a threshold method that was here used is basically you assign a threshold and then the same threshold was used for all of the animals. However, depending on how the threshold was defined by each investigator, you will end up with different uptake values, and this can result in significant changes between those different analyses. So the image analysis has a high impact on the repeatability of results, and the proper reporting of how you perform the image analysis is definitely needed in order to repeat and reproduce the data. So moving on now and focusing a bit more on image analysis. So there are multiple methods for the void placement available. For segmentation methods, you have the manual segmentation, the thresholding-based methods, but also region-based, stochastic-based, and learning-based methods, joint segmentation methods, but also boundary-based methods. I would really recommend reading the review from Foster et al. From 2014. I have the reference in the lower right corner. He defines and really explains all of these segmentation methods in detail. Within this webinar, I would just like to briefly touch the thresholding-based methods and the manual segmentation. And in regards to manual drawing of a region of interest, of course, this is very easy, but as you also have seen on the slide before, highly user dependent. So it can introduce a large variety of your results, but also it can introduce errors that you are not able to reproduce the results. So, and proper implemented automatic image segmentation methods can be more accurate and repeatable. So what I would first like to focus on are the thresholding-based methods. And this is something that I've also shown you for the left ventricle analysis from the multicenter preclinical study. So of course, it's very simple and intuitive. So basically you set a threshold and all voxels that are greater than this threshold are foreground, all other voxels are background. The disadvantages, though, are it has a large variability of pathologies, low resolution, and inherent noise. There are multiple methods available, for example, the fixed threshold, as was used for the left ventricle analysis that I've shown you before, but you can also use adaptive or iterative thresholds. And this is now an example from the literature from Pietro et al. From 2012, where they investigated the impact of different thresholding methods, so to say. So they had an original data set, and then they applied multiple thresholds. And I guess for some of them, you can already see that they completely overestimate the volume. So for example, for this one in the upper right corner, so this completely overestimates in comparison to the original data set. However, most of them look quite okay-ish, but some of them still at least overestimate at the edges. So this is when you look at these in more detail, they also determined the median, for example, and see that there is a huge range of the median of those thresholding methods. So this is something that can really impact your data. And if you use different thresholds, obviously within the same study, then you won't be able to compare your data. So moving on to the accuracy of image analysis methods. So the accuracy of algorithms, of course, needs to be evaluated. So when you develop algorithms, you also need to evaluate them. And the ground truth for this is always histopathology samples. However, if you don't have those available, you can also use phantom images that you can generate, or you can ask experts to manually segment structures on your in vivo data and compare this to your algorithm generated structures. And I would like to focus on this step a bit more. So this is an example from the literature from Hyman et al., where they investigated 12 automatic segmentation approaches and to delineate or segment the liver from the surrounding tissue. And when you first briefly look at them, they all seem to somehow catch the liver quite nicely. However, when you look in more detail, for example, on these parts here, you see that some of the segmentation methods miss certain regions of the liver. Some of them include this. And another example is, for example, this region here. So it's really something that you need to keep into account or need to keep in mind, that also you need to test your segmentation methods. And this is another example from the literature where they asked experts to draw 3 regions of the same, to draw the outline of the same 3 regions of interest on this slice. And you see already, especially with this region here, that it has a huge variability of those outline segmentation methods. So as said, histopathology is the ground truth. So when you have histological staining of the same slice of your in vivo scan available, as for example shown here. So in this case, you can have a pathologist outline based on the histological staining, the tumor region or the tissue region that you are interested in, and then you can compare it to your in vivo imaging data. So this is definitely, of course, the ground truth that you can use to evaluate it. You should, of course, use as many data sets as possible and potentially also from different institutes. So in summary now, standardization and harmonization of techniques is necessary to enhance the reproducibility, repeatability, and reliability of your data. Important, you should never change parameters and/or settings during a study. This will ensure that the data within your study can be compared. And then you need a detailed reporting of material and methods to ensure the reproducibility also on a multi-center level. And in the last 2 minutes of my talk, I would briefly like to introduce you to the RIVE Guidelines 2.0. So these are guidelines specifically made for animal research reporting of in vivo experiments. So they are intended to improve the reporting of research using animals, guide authors as to the essential information to include in the manuscript, and also promote reproducible, transparent, accurate, well-written manuscript. And I have the link in the lower right corner, but when you Google RIVE Guidelines, you will be directly forwarded to their webpage where you can then download the checklist. So this is these are the RIVE Guidelines 2.0 author checklist. So they basically have two checklists. The first one they call the RIVE Essential 10. And these are 10 items that they mention that are essential to include in your manuscript. So information about the study design, sample size, inclusion and exclusion criteria, randomization, and they give recommendations for each of this, what to include in your manuscript. But also on the blinding, the outcome measures, what kind of statistical methods you used, what kind of experimental procedures you used, and also recommendations on the results. So it's really worth looking into this and following these along when you prepare a manuscript. And then they also have a recommended set of items that they would recommend to include in your manuscript. So for example, some recommendations for the abstract, for the background, an ethical statement, but also information on the animal care and monitoring, as well as on how you interpreted your results, any scientific implications, is the data accessible, and declaration of interests. So if you follow along both the essential and the recommended set of those RIVE guidelines, this will definitely improve the repeatability, reproducibility, and reliability of your data. And with that being said, I would like to thank you for your attention, and special thanks to Ronald Ballard for providing a couple of the slides. And of course, I'm very happy to answer any questions.
Thank you very much. It was a great talk. I would just be asking everyone to have a round of applause. I'm doing it here individually, but the rest probably in the comfort zones. Right, so we are open for questions. If anyone wants to ask any questions, you can either write them in the chat and direct them to me. In case if you can't ask it or you write it in English, you can write it in Persian as well. So I will translate it in English. And if you want, you can raise your hand up and we would give you access to your microphone, webcam, and you can switch on and ask your question personally. So we have a couple of questions, Dr. Julia Mannheim, and I have more than a couple of questions myself, and I really enjoyed it. And I'm very glad that someone from Germany started talking about standardization. And well, we know Germans are a very good nation for doing everything really efficient and according to the 3 R's that you mentioned: reproducible and being reliable, and also being sort of being able to have the trying to do it repeatedly as well. Mm-hmm. Right. So the questions that we had, one of the questions that we had is from our own sort of lab manager, Miss Solgi, and she has asked, and towards the end, she asked, is there any international published SOPs for imaging? So you mentioned the RIVE, but is that just for general animal work or for imaging?
So this is for animal work, but focusing also for imaging in general. There is unfortunately not a real guideline in the preclinical field available. So this is definitely something that we are lacking and need to work on with having those initiatives in place. There are multiple protocols available for the clinical setting, though. So if you're performing clinical imaging, there are multiple of these available. However, for the preclinical area, it's usually that each lab has their own SOPs, which is good and great, so that they are able to compare the data within their own lab. However, it's really then on a multi-center level, it's still hard to compare the data in preclinical imaging, especially.
Following on, this question is actually asked by our PET manager in the TPCF, Mr. Tanha, and he has asked if there's any sort of international protocol or SOP for PET imaging, and if it's not there, why not? Why it's not there?
Well, yeah. So I like that question. Of course, why is it not there? So well, usually preclinical studies are not performed on a multi-center level. So usually preclinical studies are performed in a single institution because, I mean, you can scan 20 or 30 animals a day and then have the numbers that you need for a significant testing and so on. However, it would definitely strengthen the data if you would perform it on a multi-center level. So to have it definitely more reliable and reproducible as well. So that's, I guess, the problem, that we don't have those protocols really like published and standardized, that usually you just perform the experiments in a single facility and not on a multi-center level.
Cool, thank you very much. A question which is asked by one of the audiences, and Mr. Mahdi Muhaddisi, and it's similar to the question that I have as well, but he's asking regarding AI technology, artificial intelligence. And do you think AI could play a role for this standardization?
Yeah, well, especially in two things. First of all, the quality control to really check if your data in terms of all the technical factors is reproducible. Then also AI could definitely play a role in this, in helping to check the data in this regards, but also especially in regards to image analysis. I mean, AI is a huge field. However, as I mentioned, it is very crucial to test your algorithms based on ground truth or histopathology to really make sure that your AI algorithms are working properly. But I definitely think that by having tested AI algorithms in place, you could really help to standardize and harmonize those imaging data. Yes.
Cool. My question is actually how to perform or how to implement these standardization, especially once we have so many different parameters. And if you want to have a checklist like a hospital or something, I'm sure it's going to be maybe, I don't know, 20 pages book or something like that. You want to include all those parameters, and all these various different parts are not sort of done by one user. You know what I mean? Like looking at the animal handling, the injection, the I don't know, imaging acquisition, the analysis.
Yes.
So how to implement it?
Yeah, that's a very good question, to be honest. That's also a problem that especially labs or preclinical facilities that are starting with this have trouble with. Yeah, I would guess just do one by one. I mean, of course, making sure that the scanner works reliable, that you have trained personnel to do the animal handling. And then once the scanner is stable and once the animal handling is stable, then your imaging data will also get stable if you use the same result, the same parameters for your reconstruction and your acquisition. But I guess it's all about training and really having trained personnel, proper techniques in place, and really checking the system on a regular level, but also checking those protocols if they are still up to date or if they need to be updated. So it is not easy, that's for sure.
So my question regarding the AI, I think this is the part where AI could actually help.
Yes.
Is to use various different computer sort of packages or trying to integrate all of them together in order to, before you actually commence the experiment, to make sure all the previous things that was supposed to be done have been done correctly.
Yes.
Otherwise, as I said, if one single person wants to look at all these parameters, there's so many, and even the publications that you mentioned, it was only a few of them. I think the beautiful chart that you showed was like a circular one, That shows how complex imaging is. And I think it's not even with preclinical, even with humans, we're making loads of mistakes as well.
Yeah,
So
I mean,
that's the strange part.
I totally agree. I mean, that's also the example that I gave for the clinical study where they determined those 4 different SUV measures. So, and this can then really have an impact on the patient. I mean, that's, of course, I mean, we are doing preclinical research, but also the animals are really important to handle them in a proper way. But especially now, also when we move on to clinical imaging, this is something that can impact the patient. Yes.
Mm-hmm. So my other comment or question was like, does it mean all of our results, our positive results, are either very, very useless or very, very great that with all these differences and parameters, we still manage to get significant data?
Well, no, I didn't want to start having everyone basically checking their data, no, but or mistrusting their data. No, I think as long as you have standardized protocols within your lab, then the data within your lab is reproducible. And when you then enhance the reporting of your material and methods and your results, this can definitely then also, by just following along this guideline that I showed you, it really helps for other sites to be able to reproduce your data. And I guess this will also then strengthen your own data if your data is more reproducible. So I definitely didn't want to start everyone mistrusting the data. It's just making awareness that there need to be proper protocols in place.
True, very true. I've got a couple of questions regarding the preclinical multicenter data that you've done, and it was very, very beautiful. So one question is, did the mice that they used, did they have the same food supplier for the, maybe that
Yeah,
could
actually,
be why the
no,
glucose levels are different.
exactly. Yeah, so actually, no, because that also was basically their default imaging protocol. So also how the temperature was in the animal facility, if they have like a 12 to 12-hour cycle or like 14 to 10-hour day-night cycle. So this was all included in the default imaging protocol. So this is, of course, it's a sum of parameters. As you mentioned, it's not only one parameter, it's really a sum of parameters that can impact your results. And
And
yes, so they have different foods. Yes.
yeah, and did they have the same source of FDG as well, or was it from different cyclotrons?
It was from different cyclotrons. So each on-site cyclotron produced the radioactivity. Yes.
Mhm. And on that study, did you perform a PET CT scan or just PET scan?
So we performed PETs because all of the labs had a PET scanner available. Just some of them had a CT available. In this case, we also performed CT imaging after the PET scan, so to ensure that the PET uptake time is the same for all of the animals. And CT was just performed as an add-on that we can use it for anatomical co-registration of the data. Yes.
Yeah, because maybe that for gating and drawing the ROI, especially for the LV, without the CT can be more fiddly as well.
I
There are a
agree.
couple, yeah, there are a couple of more questions. Again, by our pet manager. So Mr. Tanha is asking, what do you think is the role of the physicist for designing and developing the standardization protocol? Or I would sort of ask his question in another way. Who do you think should come up with all these protocols and standardized sort of SOPs?
Yeah, the I think it's a sum. It should be the physicians, the physics people, the biologists. It's really a sum. I guess if you are standardizing the quality control, then more the physicist people should help in developing those protocols. But if it's more like in regards to animal handling, then I guess the biology persons or people performing the study should also have a say in this as well. Um, yeah, and especially also in regards to image analysis, the physicists might help with that one as well. So it's I guess it's, as I mentioned before, when you develop standards, it's usually a group of people that come together from multiple disciplines, so to really decide on a consensus of standards.
That's very cool. Thank you very much. Well, he was asking about regarding physicists because he's a physicist himself. He's doing his PhD in medical physics. That's why.
Mhm.
But continuation of his question, he was asking, or biologists. Right. Next question we have is from Zahra Moulay Manish, and she's asking how the standardized process in preclinical could transfer to clinical activities and research? And could the results in these two environments be sort of applicable to each other or not?
Yeah, I mean, the problem that we have in research is, especially in preclinical research, that most of our results cannot be translated to the clinics. And one of this is, or one of the factors here is especially standardization. So if we have more harmonized protocols in place, then we could potentially also enhance the translation into clinical routine. So there are, I didn't include this in my talk here, but there are over like 100,000 biomarkers developed each year, but only like a small fraction of these make it into the clinical routine. And the reason for this is, at least for some of them, that there haven't been harmonized protocols in place. So that means other sites weren't able to reproduce their data. And then also the biomarker didn't make it into the clinic. So I'm not saying that standardization and harmonization will basically solve everything, but it is a certain step, I guess, to enhance the reproducibility and also the meaningfulness of the preclinical research data.
Mm-hmm. And there's another question just came. They're asking if you've done these SOPs just for PET or other sort of imaging modalities too, and if yes, which ones?
So the preclinical imaging study, we just focused on PET. So we have in-house our own SOPs for multiple imaging modalities available, as I guess most of the laboratories have, but having them basically on a multi-center level standardized, this has not been done yet.
Mm-hmm. Cool, thank you very much.
Thank you.
There are some comments of thank you, and that's it. I'll end the session with that. Thank you very much, Dr. Julia Mannheim, and we would love to see you if you're interested whenever you want to come over to Iran. We would love to have you here and show you around, and also have a sort of, and hopefully after this COVID anyway, sort of I don't know, a talk or a presentation, but not virtually. Sort of in the
Okay,
real.
thank you. Yeah, that would be.
It was an honor to have you, and once again, I really enjoyed it myself. I learned a lot, and hopefully see more of you, and hopefully in our symposium that we have annually. And so 2021 will be our 4th annual symposium. We started with a very, very small community here in Iran 3 years ago, but now it's just getting more momentum, and more international speakers are joining as well. So we would love to have you over on that symposium. I'll send you more information sooner towards the date.
Thank you so
very
much,
Dr. Julia Mannheim. Thank you.
Thank you so much. Have a nice evening.
You too as well. Thank you.
Bye.
With that, bye-bye. I'd like to thank all of the audiences who actually joined us as well, and hopefully see you in 2 weeks' time with our next talk, which I would ask the admin to actually broadcast a poster as well, so everyone could see our next annual sort of bi-weekly TPCF webinars. With that, I would end the session, and thank you for attending this evening's session. Thank you very much.